Tackling congestion in VLSI design, showing the question. Congestion, a critical challenge in VLSI physical design, arises when there's insufficient routing space between circuit elements. Here's how to address it. Understanding congestion. Definition. Congestion refers to the inability to route wires due to lack of available space. It can lead to longer wires, increased delay, and potential design failures. Congestion mitigation techniques. Floor planning optimization. Macro placement. Strategically place large macros to create wider routing channels. Channel width adjustment. Increase channel widths in congestion-prone areas. Core shape modification. Reshape the core area to provide more routing space. Placement optimization. Congestion-driven placement. Utilize placement tools with congestion-aware algorithms to distribute cells more evenly. Cell padding. Introduce spacing around cells in congested areas to reduce local density. Blockages. Define soft or hard blockages to prevent cell placement in critical areas. Routing optimization. Iterative refinement. Run multiple placement and routing iterations to improve congestion. Congestion-driven routing. Use routers with congestion-aware algorithms. Wire length reduction. Employ techniques like wire bending or jog insertion to shorten wires and reduce congestion. Design rule relaxation, cautious. Consider slightly relaxing design rules in specific areas, with careful evaluation, to provide more routing space. Additional techniques. Feed-through insertion. Introduce feed-through cells in congested areas to provide additional routing paths. Hierarchical routing. Break down the routing problem into smaller, manageable sub-problems. Power and ground network optimization. Ensure adequate power and ground distribution to prevent additional routing congestion. Tools and analysis. Congestion maps. Visualize congestion hotspots using EDA tools to identify areas needing improvement. Statistical congestion metrics. Analyze congestion metrics to track progress and evaluate the effectiveness of mitigation techniques. Conclusion. Congestion management is an iterative process requiring a combination of floor planning, placement, and routing optimizations. By carefully considering these techniques and utilizing advanced EDA tools, designers can effectively address congestion and achieve successful VLSI designs. Fixing timing violations before CTS, showing the question. The question you asked is fundamental in VLSI design. Addressing timing violations before clock tree synthesis, CTS, is crucial for overall design success. Here are some common techniques. Understanding timing violations. Setup and hold times. These are the primary timing constraints for flip-flops. A setup violation occurs when data arrives too close to the clock edge, while a hold violation occurs when data changes too soon after the clock edge. Pre-CTS timing violation fixes. Logic optimization. Restructuring. Simplifying logic by reducing the number of logic levels can improve timing. Retiming. Moving logic stages between flip-flops can help balance the timing path. Library optimization. Cell sizing. Using larger cells can reduce delay but increases area and power. Library characterization. Ensuring accurate cell delay information is crucial for reliable timing analysis. Clock path optimization. Buffer insertion, limited, while not ideal before CTS, strategically placing buffers can sometimes improve timing, but overuse can lead to increased power consumption and skew. Constraint management. Relaxing constraints. Temporarily relaxing timing constraints can provide more design margin, but should be used cautiously. Tightening constraints. Identifying non-critical paths and tightening their constraints can focus optimization efforts on critical paths. Limitations of pre-CTS fixes. Ideal clock network. Before CTS, the clock network is assumed to be ideal with no skew. This can lead to inaccurate timing analysis. Hold violations. Fixing hold violations can be challenging before CTS due to the lack of accurate clock information. Importance of post-CTS fixes. Most timing violations, especially hold violations, are addressed after CTS when the actual clock network is known. However, pre-CTS fixes establish a good starting point for the design. Conclusion. While some timing violations can be addressed before CTS, it's essential to understand the limitations and focus on improving overall design structure and logic. The majority of timing closure efforts occur after CTS when the clock network is defined. By carefully considering these techniques and working closely with timing analysis tools, designers can significantly improve the chances of achieving timing closure in their VLSI designs.